we present our work, learning to segment rigid motions from 2 frames. Our goal is to decompose a scene into a background and multiple moving instances based on their rigidity. Given 2 consecutive frames, we design a neural architecture to jointly regress the background pixel mask and rigid instance pixel masks from the measured 3D motion field. Then, the motion of each component can be parameterized by a 3D rigid transformation as shown by the blue and red arrows, where blue designates background motion relative to the camera. Such decomposition is shown to be useful for 2-frame depth and scene flow estimation. Classic geometric segmentation methods decomposes the scene according to camera geometry and scene rigidity, but are sensitive to measurement noise and are not able to detect certain kinds of object movements, such as incoming cars moving parallel to the ego motion translation vector. We stress that none of these results are smoothed over time. Appearance-based detectors fire on every object, but are not able to distinguish objects that are actually moving from static objects that are able to move. Furthermore, they rely on appearance cues and fail for novel object classes not in the training set. In contrast, our method is powered by geometric reasoning of when independent object motions can be detected, and therefore generalizes to novel appearance. It also adopts a neural architecture trained on a large synthetic dataset, and demonstrates robustness to noisy inputs and degenerate motion configurations. Our paper includes a theoretical analysis of what kinds of object motion can be detected. Here, we analyze the 2-frame sequence of a car moving towards us. It turns out there is a rigid interpretation of the scene that is completely consistent with the ground truth 2D flow. The car is not moving, but is fixed at floating position above the ground. Note, under the classic Sampson distance criteria visualized at the bottom left, the moving car disappears because its movement is consistent with the epipolar geometry. We use our analysis to define several motion models that will be fed into a neural architecture for decomposing a pair of frames into rigidly moving components. Notably, our architecture does not make use of appearance cues, but instead makes use of motion and depth inputs computed with off-the-shelf networks. Our architecture has 3 main steps. First, camera motion is estimated from optical flow using a differential variant of the 5-point algorithm. Then we compute estimates of pixel rigidity according to the estimated camera motion and 3D scene flow. These motion inputs are fed into a segmentation network that outputs instance masks of the rigid background and an arbitrary number of rigidly moving instances. Each object is represented by its center location and polar shape coordinates. Finally, we fit rigid body transformations within each rigid mask and update the depth and 3D scene flow. We train our segmentation network on a synthetic scene flow dataset. On Kitty, compared with geometric rigidity estimation, such as motion angle, our method successfully detects incoming cars. Compared with appearance-based methods, such as point wind, our method correctly segments the parked cars together with a rigid background. Our method also produces state-of-the-art 2-frame depth and scene flow estimation on Kitty and Centel, significantly improving over prior art. Our method also generalizes well to novel scenes, such as coral reef scenes. Compared with geometric rigidity estimation, our method is more robust to noise in camera pose and flow estimation. Compared with appearance-based segmentation methods, our method successfully segments the rigid background and moving faces, while reconstructing the scene at the same time.